This meeting is being recorded.
In section 6, we will introduce the next characteristic of our signals in an NMR spectrum. So we've looked at the number of signals and then the chemical shift. Now we're going to take a look at what's referred to as the integration of our signal. So we see some signals shown here on our spectrum. So we have 4 signals total, and each of which has this integrated area below it that we can use a computer program to calculate. So we see this step curve, this red curve here is referred to as a step curve, which is used to integrate or find the area under the peak. And that will tell us the relative number of protons giving rise to each of these signals. So let's here take a look at these integration values. So we see 27, 0.0, 40.2, 28.4, and 42.2. So again, this will show us, based on the integration, the area under the curve, and then we can set the lowest area. So our computer operator here, whoever's running these data, can set this peak here, this integration value rather, to 1. So that's the one shown here. And then everything else would be relative to that 1.0. So we would divide, right, 40.2 by 27.0, and we would get about 1.48, and like so. Divide this by 27 and this by 27. So now we see these relative ratios, so 1 to 1.48 to 1.05 to 1.56. And if we were to double these values, we would end up finding that this first peak here would actually be representative of 2 protons. This one would be 3 protons. This would be 2, and then this would be 3, until we reach these numbers that are very close to whole number integers. So again, we have about 2 protons, 3, 2, and 3, and each of these signals. So sometimes integration and these relative quantities cannot determine the absolute count of the number of protons. So at times you can, but if there's symmetry within a molecule, that's one time where we would see that our relative integration would give us 2 signals that in this case would be 2 to 3 in proportion. But we know that we have 4, right? If we drew these protons here, to 6 in our ratio, because we have each of these 3 and each of these 3 protons due to symmetry, giving us that other signal. So we have 2 distinct signals here, 2 distinct kinds of protons, but our relative integration value would show us this 2 to 3 ratio, which we know is not the absolute count or correct number of protons. So at times, we need to know the molecular formula in order to know the absolute ratio. So here we know that our absolute ratio is 4 to 6, but from our integration values and then our conversion to find out that ratio, again, we would be lost in only thinking that we have this 4 to 6 ratio instead of, or I'm sorry, this 2 to 3 ratio instead of what we actually know is a 4 to 6 ratio. So we'll look at a variety of practice problems that utilize this characteristic of integration.